All right, we are back. And now it's my pleasure to introduce Andre Alexandrescu. He's a research scientist at Facebook. And I don't think he's met a template he doesn't like. And he's going to come here and blow our minds talking about one of C++11's most important features, arguably, certainly for Stefan, Variadic templates. Please, a big warm applause for Andre Alexandrescu.
Thanks. Thanks very much for inviting me to the organizers. Gotta say, there's a lot of work going into the organization of this all. It's from the backstage, it's pretty much like a military operation. It's very specific and very clear organization. They aren't that efficient as C++ is. And I gotta say, so today, generally I like to project this cool demeanor. Emotionless guy, but I gotta tell you, number one, so we have the Bjarne speaking. Number two, we have Hans Bohm, the consummate researcher, probably wrote more papers than I read. Then we have Stefan, who's this awesome hacker and the fastest speaker I could ever follow. And then there's you, and how would you feel, right? So my heart is pumping real hard right now. And my stomach hurts, and then I looked on Twitter and said, there must be people who still, I must have fans out there. I think that word is misspelled, actually. I'm not sure, really. Alrighty. Well, with this, let's proceed. And good spirits. I'm going to talk about three things. Motivation fundamentals of Variadic templates. We're going to go through the steps of implementing a true Variadic function, see exactly what it takes to make the sausage of a true Variadic function, which is a bit more difficult than it could. And then I'm going to discuss a bit about std tuple, and again, what sort of tricks go into it. Once we make once we do these exercises, I'm sure we all will be very well equipped to tackle very interesting problems that can be solved with Variadic templates. All right. So the motivation behind Variadic templates were, first of all, we had this desire to define types of Variadic functions. We've had this desire forever. Printf being like this absolutely archetypal function that is very fast, very good, except it's extremely unsafe. And probably, I'm not sure about you, but I passed the wrong arguments to printf. And I was very thankful to see that modern compilers introduce, at least when you pass a literal string in there, they're going to take care of it, and they're going to warn you that you're not passing the right types in there. Actually, two more, so you pass a size t. I don't know what the hell that is. Right, so it's size t is like %z. Write that down. All right. So you want to do function forwarding. You want to forward, like I want to log a function call, and that function should take any number of parameters, just adapt itself. And we want to do logging before and after, for example. That's a nice motivating example. We want to define the so-called algebraic types without contortions. I think they are quite popular right now, variant and tuple. Variant would be a sum type because it can hold one value of a given type at any time, but only one. What's a variant good for? For example, a database column, right? A database field, which is essentially dynamically bound. You don't know the exact type. Inheritance is not the most appropriate mechanism for that because the universe of types in a database is, is limited, is known, is finite. So it's very good to have a sum type there that represents any of those elements of that universe. Tuple would be a product type, which would hold a juxtaposition of different values of different types, arbitrary long and arbitrary values. And then I'm not going to insist too much on that, but I'm going to talk a bit to specify settings and parameters in policy-based design, a subject that is, of course, dear to my heart. All right, fundamentals. It starts very easy, doesn't it always? you may define a template class that takes type name dot dot dot. By the way, type name can be replaced with class, but it kind of came back on vogue since the dot 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 came about, because class dot 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 is not one or more classes, more one or more types. So it's type name dot dot dot, or you can define a function that takes type dot dot dot. Next slide is this slide is essentially very important for our understanding of traits of template variadic. So it's extremely important. It's the key to understanding variadic templates is to understand that in the examples in these examples, T's and V's are nothing you know about. It's a new kind. These are new kinds. They're not types. They're not values. They're like nothing in existing C++, in C++ without variadics. So T's is not a type, and V's is not a value, right? So you can't say, well, let me create a local type there for T's to give it a different name. You can't do that. You also cannot say, let me make a copy of these values, these parameters. Let me make a copy real quick here. That's also not going to work. You cannot even instantiate that type at all. So T's and V's, these are new entities, new kinds, right? Therefore, they're going to obey new rules. So forget everything you know about what applies to regular entities in C++. We're dealing with a completely new universe here, right? All right. An interesting detail, either T's or V's may be actually potentially empty. And that becomes bizarre once you start to talk about things that are empty and they have a name, however. So, we're going to treat them differently. And in particular, there's exactly two things you can do with them. Number one, one is useless. So there's one thing that's useful and doable. The useless thing is size of dot dot dot. You can apply size of dot 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 to a list of types or a list of values, and what do you get back? You're going to get back the number of elements in the list. It's not the cumulative size of the entities in that list. It's actually the number of elements in the list. Potentially confusing, but that's not the point. The interesting thing is this is not doesn't need to be a primitive for a simple reason. It could be actually done in other ways. The important operation you can do is to expand back the list. And look at this example here. I have a laser. Look at this example here. So we have a function that takes, so it's parameterized on T's, a list of types. And it says, well, I'm going to take, the spaceship era or whatever, the Twitter era, double ampersand, which is our value reference, and it's going to take a list of values. Now, here's what's going to happen. Inside this function, it's going to forward to another function. Just for the sake of example, it adds a new argument, this floating point value, and it adds a floating point value at the end, just because I can. And here, this is the interesting part. The interesting part is we apply the expansion operator, which is very fittingly dot dot dot. And what's going to happen here is that dot 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 is going to expand everything that is to its left in a ways that we're going to explore. Okay? So this is the expansion operator. And what's going to happen is that it's going to essentially expand the list. What do you think happens if you actually pass an empty list? You call fun with no arguments. Well, something very interesting is going to happen. And this is going to reveal that it's sort of not textual expansion. It's smart textual expansion. You see that? You see this comma here? Right? We have a comma here. And we have a comma here. And if we used textual expansion on the empty list, nothing would come here. And we'd have two commas in a row, right? In reality, one of the commas, I don't know which, is going to disappear, right? One of them is going to disappear automagically. This is part of the expansion magic, right? So essentially, it's not textual expansion, although for the most part, you can think of it as one, as I'm going to explain next. So there are certain rules that apply to expansion, what you can expand and in what context, right? Number one, we have this dot, 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 and where this is a list like we just discussed, it expands into the comma-separated list. Now, here's the thing. Do you have sharp eyes? Because I got to tell you, the font here and the font here, they're different. I'm not kidding. This is Courier New, and this is \shell dots in LaTeX, which is essentially, it's a sans serif font in this, on the slide. So this is actually the literary dot, 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 the ellipsis. Okay? It's the, it's the elements of style dot, dot, dot. And this is the actual punctuation in the language, dot, dot, dot. All right? That makes it a bit difficult to discuss things, right? All right. So, very simple. We start very simple. This dot, dot, dot expands into the actual, the actual list of the types. Second, I'm not kidding anymore. Don't laugh. No more laughs. All right. Second, we could have a qualified types and the type with adornments, like, reference, const reference, etc. is going to expand very nicely to like qualified list of individual elements. Beautiful. So we start with a qualified type with adornments star, ampersand, double ampersand, and it's going to expand very nicely as expected. Even better, and start carefully here, because we have a sort of a complex construct here involving a type, a list of types, and the regular type y, and you access even a member, and you put dot, dot, dot after it, and as I said, dot, dot, dot kind of cleverly looks to its left and expands whatever can be expanded, and very nice, it discovers that y is fixed and this is variable, and therefore it's going to expand it cleverly as shown, right? So this will be the third expansion rule, okay? Even more interesting if you have two lists of types, T's and U's. You notice I'm using this convention like T's and U's, so the suffix S is like plural, right? T's and U's, and one happens to be adorned, dot, dot, dot. Well, guess what? They're going to expand in lockstep. They're going to expand in lockstep. Okay? Very interesting. And finally, last but not least, we have a function call that's going to, for example, it uses some, some non-variadic stuff, and it also has some variadic stuff. It's going to nicely expand into, like applications to each element in the list of values. Very nice, right? Okay, so these are expansion rules. So it tells you what you can expand and what it's going to expand into, right? And then there's the converse element, which is, where can I expand things? In what context can I expand things, right? So the places where I can actually expand things are an array initializer. I can expand stuff. In a base class specifier, which would go like, template type name dot, 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 tees, struct C inherits tees dot, 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 which means inherits, from everybody, right? Then we have template of type name dot, 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 tees, struct D, you can actually say box of tees. Maybe you want to have some integers here, some primitive types that you cannot inherit, so you box them. So I'm going to inherit box tees dot, dot, dot. And per the expansion rules that we just discussed, this is going to expand nicely as expected, right? All right. And we can, at some point, so we have this guy here, and maybe we want to initialize it. Well, guess what? You can actually expand inside the member initializer list. So imagine we're inside the struct D, and we say template type dot, 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 use, which is a different thing, and we have D taking use, and it forwards them to box of T's. dot, dot, dot. So this is going to expand nicely. And there's 3 more. 3, not 4. There are 4 bullets, but there's 3 things. I'll explain. Okay, actually, let me get, exception specifications. Variadic templates work with exception specifications, but exception specifications are gone from the language. So this is sort of one of the false implies anything kind of thing, right? I know they work for a fact, and nobody can contradict me, right? Because nobody can prove anything, right? False implies anything. All right, so let's get rid of that guy. So in template argument lists, it's quite interesting. You can actually expand. And in this case, we know that map takes 2, 3, or 4 arguments, right, in its parameterization, right? So this is going to work if this happens to be 2 elements long. It's going to work if it's 3 elements long. It's going to work if it's 4 elements long, but nothing else, right? So this is, this is an interesting example. It just works with certain lists. Attribute lists, I am from the future because there's no attribute that can expand that way. So this is a sort of, it is in the specification, but nobody can use it yet because there's no attribute that's expressed as a type. Finally, capture lists. And this is actually very interesting. Let's take a look. So we define a Variadic function fun. It takes these v's. And guess what? I define a lambda that decides to capture the entire parameter list of fun, whatever it was. 0, 1, or more values, right? Parameters. So it's going to capture all these guys by reference, and it's going to do whatever, right? Forward it or whatnot. So this is very interesting because it allows you to define some sort of interesting, I want to store things somewhere and work on them later and that kind of stuff. Very good for threads, for example. All right. Please note, expansion proceeds inwards, outwards. This means I'm dealing with 3 expansions here. All right, like in those games, like there are 6 little differences between these 2 drawings, okay? There are 6 little differences in between these 3 calls because the first call, and believe me, I rehearsed this, it's difficult. In the first call, I'm expanding all t's for instantiation of class A, and then I'm going to call Han of v's, and this is going to be all all elements expanded once, and then I'm going to expand again in passing multiple parameters into gun, right? By the way, so I'm very sorry I didn't have the time to modify. I loved Stefan's meow and examples. I'm going with fun, gun, and Han. So not as attractive as it would go. So okay, but be careful here. The dot dot dots is where the fun begins, because so first I expand this guy, and here I expand, and after I expand this guy, I'm going to expand for each value. I'm going to expand again. Second call, notice that I move the parentheses here. You see, I mean, this is going to cause the Venus probe failure, okay? If you put the parentheses in the wrong place here. So this is going to expand all t's and all v's separately, right? It's going to expand all t's and expand all v's. This is going to be a of int float double, Han of 2.3, 3.4, right? And the third, which is the most interesting, is going to expand things in lockstep, because it's going to expand the first argument first, and then the second argument second, and the third argument, and so on, right? It's going to expand t's and v's in lockstep. Does it make sense? All right. Yeah, no answer. All right. So very careful here. So actually, homework. Where's the Twitter stream? Homework. Get the Cartesian product. It's not difficult. Can be done. Can actually express the Cartesian product of a list against itself. You can get all combinations of a list of types. Like, the outer product. Pretty crazy, huh? All right. Well, even better, since I became a sort of roadshow attraction, like, oh, you know that guy with the elephant man, the guy who shows you like difficult templates. Well, I'm here not to disappoint, earn my free food. All right, so this is actually works. And let me actually give it a name. I'm staking the ground here. VVTTs, which is Variadic templates. And now, honest, I removed the slide from the deck, and I was asked expressly. They said, you know what? We're not paying you your hotel if this slide must be in. Therefore, it is in. And the way this works is we have a template that has some, let's say, fixed parameters, such as t here, just for example's sake. And the interesting part is that I then parameterize it with a variable number of policies, each in turn taking a variable number of arguments. It's extremely flexible. What? Okay, so this was involuntary humor, I swear. I didn't. Okay. Well, this works. All right. So, question. Well, since we have so few rules for expansion, how do we actually use this thing? And let me actually give you a simple example. Is one of, which goes as follows. Is one of, we write two specializations for it. And the first takes 2 arguments, and the second takes 2 or more arguments. And in the first case, we say, well, is one of A, B, or returns if A equals B, The second is more interesting because it takes T1, T2, and some more other types. And it takes A, B, and some more other values. And then it says, well, return, A equals B, which is the head comparison, and then or recurses to itself, right? Is one of A, and then passes the tail of the arguments to the thing. Now, okay, so don't get, okay, just as an example, assert is one of 1, 2, 3, whatever. So it's going to compare 1 against 2, then 1 against 3.5, 1 against 4, and finally it's going to compare 1 against 1, it's going to succeed, right? And, as you know, like today's compilers have gotten very good at inlining and whatnot. So after the dust settles, this is going to be really a lot of just comparisons and jumps. I actually looked at it. It is efficient, right? However, don't get confused. This is not recursion, right? This is not recursion. It's same name. It just so happens there are multiple functions with the same name, but they're unrelated as far as address, for example, right? So this is not true recursion. It's a sort of compile time recursion because we are never asking. We're never recursing to is one of with the same number of arguments. All right. Now let's look at printf. And printf has a lot of good things about it and one bad thing about it, right? I love printf. I've used it all the time. So it's fast. It's thread safe. All that locking and unlocking the string, the file handle underneath. It's very convenient to use. Everybody knows the formatting strings except %z. It's known by everybody, but it's very unsafe, which is a problem. I've seen on Reddit only the other day. Printf can be used to gain root access in sudo, right? Sudo, and it's important. It's an important utility. I use it every day. And if you pass it a formatting routine, % something to it, it's going to not do good things. So definitely it's a problem that we'd like to address. If you go and look at, for example, you look Variadic templates, you're going to see examples of printf re-implemented in a Variadic way. And everybody does it wrong, except yours truly. Because what I'm going to do, I'm not going to re-implement printf from first principles, because that's what everybody does. No, printf was great. Just add safety on top of it. Just add a checking step, and then let it run. It's going to run full speed. Even better, if I feel cocky, I'm going to go I'm going to run the test only in debug mode. I compile, everything, so I know it works, and then I'm going to, in release mode, there's going to be unchecked, right? Awesome. Step number 1. First, we need to add some adaptation routines. I call them printf has some, this dot 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 in printf has some weird rules. All integrals become long. All floating points become double. All that stuff, right? So here's what I'm going to do. Well, I'm going to use this enable if idiom, which I'm going to talk more about tomorrow. And I'm going to say, well, you know what? If this type is integral, it just return a long. Convert it to a long. If the type is floating point, then I'm going to return a double. And finally, this is the more interesting part. If it's a pointer, just leave it alone. And the interesting part here is, well, if you just pass a string, let me extract the char star from it, right? Because this is what you want. When you printf a string, what you want is actually access the pointer to character from it and just print that as a raw zero terminated string, right? Very nice. OK, so normalized argument. It just passes the argument through a simple filter that actually does the a little type adjustments, so to say, right? And I feel audacious enough to actually run a little test, and it works. So I say, well, safe printf, but it's not yet safe. It doesn't do any checks. But it does work because I pass everything through normalized argument, and everything works. Very nice. I actually run the code, which is very unusual for me. I ran the code. It does work. All right. So far, so good. Now we're going to step 2, which is, OK, so let's actually define the base case, which is printf with nothing, no arguments. It's just the string. Well, what we need here to do, it's just some simple straight code, which what it does is just to verify that I don't have a formatting percent, because there's no argument, so I'm not supposed to have any, right? I can have 2 in a row, right? 2% in a row. That's legal. Everything else is illegal, right? Good. That's what that does. Very simple. And now, careful here. We're going to the sort of the recursive case. That again is not real recursion, right? But we're going to the recursive case where the way it works is, well, check printf. OK, so let's see. We have the formatting argument, the formatf. We have the first type, the first value that you pass to printf, and we have 0 or more, right? Extras. And then, well, we're going to iterate through the format string, and we do this same duplicated percent sign, whatnot, continue. Nothing interesting. Here's the interesting part. At some point here, just before the switch, we found a percent followed by a letter, right? Followed by something that's not a percent. So we say, well, let me see what's going to happen. If it's an F or a G, that's a floating point thing, right? I'm going to enforce at runtime that is a floating point. This is my check. This is my payload. This is the essence of it all, right? If it's S, you gotta check it's a pointer to character, and so on and so forth, right? And by default, if nothing fits, you just throw an exception, right? By the way, just as an anecdote, I had 10 years of C++ behind me when I found that the default can be put at the beginning. I always thought it was got to go at the end. No, it doesn't. You can't put it anywhere you want. It's just a label. 10 years. All right. So this is my check. Enforce here. It's the payload. Enforce means if it's not, throw, right? And this is the recursive step when I say, well, let me actually bump past the formatting character. So ++f. I'm bumping. I'm done with it. Bump the formatting string. And then pass the tail, right? And with this, I'm done with T, and I continue with T's, and whatever is left from the formatting string, right? So this loop, actually, it's a sort of a funny loop. It doesn't go through all the entire formatting string. It only goes for as long as, until it finds an argument to check. At that point, it stops, does the check, and then recurses to itself, a different version of itself to finish the job. Make sense? All right, and in the end, it just so happens if we did, if we did go through the entire formatting string and we're done, there's still this T here, this argument here that's not formatted at all, so we're going to throw an exception, too few format specifiers. So I have all the checks very nicely done in, I swear, you can fit it on slides, which is quite a trick, right? So check printf. So we have the base case. We have the recursive case. You need the base case because, again, at the end, you use the recurse, you reduce, and at the end, you come with a format without anything, right? Awesome. Step 4 integration, very simple. Check printf, right? Very simple. There's really nothing else to it. Very efficient. And actually, we could, again, I told you, like we can say, well, if and def and debug, all those good things. We could extend to other types. We can allow, can add flags, and this is really simple. It's just the basic formatter. So we could add flags and precision, and all those good things that printf supports in its format string. We could allow odd cases, such as some people actually pass along and expect to print it with a pointer format or vice versa. Those should be allowed. There's no harm in doing it. You could define safe scanf, which is even better because scanf is even more dangerous to get wrong, and so on and so forth. So much about printf. Let's get a bit into std tuple. So std tuple is sort of the flagship offering of std, of C++11, that uses Variadic as a core facility, right? Again, it's a product type that packs together any number of values. So you can say, I'm using a tuple of int and double. I'm using a tuple of int, double, and string, and so on, right? Any type combination. It plays nice with std pair. In fact, tuple of 2 arguments have our special case to behave more like pair, have the pair primitives, and so on. Very nice. What's not so nice, in my opinion, and I'm very happy that Björn and I had a long discussion yesterday, in which this kind of sort of like, oh my God, I can't believe we think so much alike. But probably he didn't think the same. He said like, oh, I'm so bored. So we had this conversation yesterday about how important good layout is to C and C++, and how important it is that C++ actually builds on the bedrock, the foundation that C puts together. It's a wonderful model because it allows you, where objects are, where stuff is. You can put bricks together, right? There's no house that has a brick here and a brick in the next neighborhood, right? Like with a pointer in between, right? So there's no house like that. It's the bricks come together, and that's beautiful. And the whole way, the pointer arithmetic, the way objects are laid out in memory. And it's so easy to understand and so easy to use, and so efficient because there's absolutely no middleman in your interaction with memory. This is wonderful. So apologies for the parentheses. Getting back to this, the issue here is that in tuple, store layout is not specified. So anybody can choose any layout. So if you have a tuple of int, double, and string, you don't know where they go, right? They're going to be contiguous, but you don't know exactly where they go. And it turns out that everybody puts them in the wrong way. And let me just give you a short, introduction to std tuple. Let's say we have a tuple of int, string, and double, and well, we can assert that tuple size of tuple's type is 3. And then we can say, here's interesting. So get 0t, you can assign to it, which is this int. You can say, assert the obvious. Get 1t gets 42, and so on, right? So you can read and write using get template, and you just pass the index of the element 0 based into get's template argument. All right, why do you think it's not t.get 0? I'll explain in a second. So the usual suspects are there. You have a bunch of constructors, you have assignments, you have move constructors, you have move assignments, all of these good things. There's a function make tuple that uses argument deduction, so you don't need to write tuple of blah, 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 blah. You just say make tuple and just pass the arguments. It infers the types for you. there's comparison, swap, and again, the usual suspects. Not so usual suspects, I'm not going to discuss this so much because I'm going to focus on get. We have pack arguments, we have tie, we have tuple cat, we have allocator constructors, uses allocator, and some range primitives begin and end. I'm not sure everybody implements all of these. Actually not, yeah. All right. So the structure of the tuple is as follows. So we define the base case first, and it's like template class dot dot dot. As I told you, class and type name are interchangeable. Class dot 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 tease, class tuple does nothing. And so that would be the empty tuple, because the specialization for non-empty type lists goes like this. Template class head and tail, T and T's, right? Says, well, I'm going to define tuple of T and T's to inherit privately tuple of fewer elements. Why are we using inheritance? Because we want to take advantage of the empty base optimization, such that when the tuple becomes empty, this is again recursion during compilation. So when the list of types becomes empty, we want to not pay for that empty tuple at the end. So this is a sort of a common idiom by now. Why private? Because we don't want to, we don't want people to assume we're using a specific method here. And privately, I'm going to add more state, because I need to put the head somewhere. The tail is already there in the form of the base part, right? And we need to add this guy, the head. Good. Question. What's the layout of this guy? Well, it turns out it's exactly, just like in Stefan's example, is the exact opposite of what you'd expect. It's reversed, right? So if you have tuple of int, string, and double, the double is going to be first, followed by the string, followed by the int. That can be a bit unexpected, right? There are techniques to reverse this list of t's and get it in the expected order, but I'm not going to be concerned with that right now. This is legal, okay? Layout not specified. Personally, I prefer to have a specified layout in which there's the prefix property, which I think is very useful to a lot of applications. All right. Now, let me actually skip a slide forward here. Let me explain you why get cannot be a member. You don't want get to be a member. Because if it were a member, you'd have to write .template everywhere. Right? And that's not something that people who are not me want. Right? I like it. .template, well, yeah, I love that. All right, so it's like I'm like a dog when you whistle, and like, yeah, template, good. All right, so, but with that being said, I accept that there are people out there who don't like this, so definitely get better be a free function and takes the tuple and problem solved. By the way, the reason for which this .template came about is because of a very old issue with C++ is this less than sign here. You see the laser? Is the laser visible? So, get less than 1 here. And if it weren't for template, there would be t.get less than 1 greater than open paren, close paren, which is sort of a bizarre construct. But if you put something inside the parentheses, it would look legit. It looks like two comparisons, right? And there's a lot of code that would be ambiguous that way. To disambiguate, you need to write .template. To get rid of that template, we may get a free function. So, that's now, you know exactly what's going on, right? Okay, so let's implement this get thing. To implement get, first we have a lower ambition, a smaller ambition. Let's just implement, give me the type of the element of the kth element. Like I have a tuple with 5 elements, give me the type of the third, right? And we can get this done by, again, a simple recursion. So we say, well, template size t and class struct tuple element. This is sort of the incomplete declaration. And then we say, well, template of head and tail, class t and class ... t's. And we go, well, tuple element of 0 and the tuple, bingo, it's the first element, 0, right? Bam, we return it. It's the type here. We just type the filter symbolically. Awesome. If it's not 0, which is implied, this is, this specialization is going to kick in. Well, if it's not 0, this is going to kick in. So k, head and tail, and we have tuple element of k, blah, blah, blah. And what we do is we recurse, just like in the Lisp, the classic Lisp example, whenever you want to find the length of a list or the kth element in a list, you sort of kind of reduce successively the list and recurse. This is what we're doing here. K minus 1, and we take the tail. Right? Very nice. So what we got so far is, you give me a tuple, you give me a number, I give you the type of the element at that position in the tuple, right? This is an important building block because this type is the return type of get. This is what when I call get, this is what I get. Sorry for the ambiguity there, right? So whenever I call get, I need to say get returns this. Well, this is it. To wit, we start with the specialization for K0. And again, I'm using this, I'm availing myself of enable if, which you can think of as a sort of a way to restrict the template from kicking in, right? So I'm restricting it to k equals 0. So if k is 0, this works, essentially. And if k is 0, I'm going to return type name tuple element of 0 and tuple blah, 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 reference. Because I'm returning the reference because, remember, I can assign to it here. Where is it? Yeah. I can assign to the thing here. So I return by reference. I return an actual reference to the object sitting inside the tuple. Right? I'm not returning a copy. So, where were we? Here. Here. So we say, well, if k is 0, then definitely we just return the head of the tuple. We're done. Because k is 0. What do you think is going to happen when I want to return the kth element? Well, recursion. I enable it if k is different from 0, is non-zero, right? And in that case, I'm going to say, well, returning tuple element blah, 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 reference. I'm returning the reference thing. And then I say get blah, 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 and then I recurse to get k minus 1. Right? Now, here's a subtlety. There's all this business with I'm taking the super and all this stuff. Here's what happens. Remember when I define the layout, I very carefully use private inheritance here. Which means whenever I have a tuple of 5 elements, it's going to inherit the tuple of 4 elements and it's going to add something to it. The tuple of 4 elements is going to inherit the tuple of 3 elements and add some more stuff to it, and so on, right? So we have this nice layout property. It's not the prefix property, it's the suffix property. So the good tuple has its own smaller tuple as a suffix, right? As a prefix, sorry. So I'm exploiting this by doing this here. Here what I take is really the base type of the tuple. This would be the tuple without the first element. And I rely on the layout to say, I have a tuple of 5 elements, and I'm asked for the third element. Well, I reduce the tuple to 4 elements, and then I request element minus 1, right? So this is the idea here. I reduce at the same time the application size and the index that I'm requesting. So that's this recursion here. Again, it's not true recursion because I'm not recursing to the same function. All right. I hope so. This has been like sort of the tableau vivant of this talk. So kind of the apotheotic finish. With this, I'm going to summarize. So, whenever you want to use Variadic templates, what you're going to do is use the familiar approach, which is you match pattern and you recurse. We've been using this with templates for a long time. We've been doing this for a long time. And the nice thing is that now you can do it like with variable size list of parameters, which is great. So it just, pattern match and recurse. We've done this a few times in this presentation. What is new is the expansion rules and low-C. There's some very restrictive things you can do against like list of types and list of values. And the expansion is smart because, again, it eliminates the sort of undue commas and all that stuff. And what you need to remember is that whenever you use one of these parameter packs, one of these list of types or list of values, what you need to do is immediately expand them into something else. So you apply the expansion rule, and then you figure out what you need. True variadic functions are finally possible, which is a great thing. I love the printf that's variadic and safe. And finally, std tuple is a useful abstraction for product types. I asked Alice there, Meredith, what happened to variant? Why is it not variant in the standard? He said essentially there's so much people can have had the time to do. So definitely there's variant in Boost and elsewhere. So definitely it's good to have, and std tuple is a very good flagship example of what variadics can do. All right, with this I'm done and I'm ready to take questions. Yes.
Thanks. With tuple, you had to do interesting base class tricks and recursions and things. Well, not quite recursions. Why is it that it wouldn't be possible to expand the parameter pack as a member?
So the question is, why can't I expand the parameter pack as a member inside an object or as a...
Or even as a local inside a function call, for example. Right. I can have variadic function calls, but I can't variadically construct an object.
You can move your hand because I can't hear.
Sorry.
Okay, so why can't I just put, do this like which we had in the beginning here, which was... Good, I don't have many transitions here. So you meant this, right? Why can't I do this?
Right. I suppose I would have expected a ... there somewhere, but yeah, I would expect a say var to become its own
I think
pack.
the answer, I think I understand the question. I think the answer has to do with reaching paradoxical cases. Because very often when you have a list of types or a list of values, you don't know, do I want to expand this right now or not? So they prefer to say, let's make the expansion explicit as opposed to implicit, because otherwise you'd have paradoxical cases. Imagine you want to expand an empty list there. Herb has a
also, what
addendum.
What would their names be?
What would their names be? Well, what would their names be? It just append the suffix 0, 1, 2. Okay.
Well, I would assume it could potentially work the same way as the parameter that I pass to the function that's a variadic pack.
Here's the thing. So let me actually let me qualify my answer. I believe the design you mentioned is feasible, is doable. This is just as legit as that, right? So this is a different design, right, in which expansion is explicit. But I'm telling you, in every design, because we've done the design in the context of another language which shall remain nameless. We've done a different design in which it's the other way around. So non-expanding is explicit and expanding is implicit. So you can go either route. Yes. Yes.
2 quick questions. The first is, why can't you use auto to infer the return type of get in the declaration? And the second question is, couldn't you change the storage order by using composition instead of inheritance?
Yes. Question number 1 was, why don't I... Apologies for that guy. All right. Why can't I just use auto here? Here, right? Why can't I use auto? The answer is, it didn't work with GCC. Right? It's a practical answer. I told you, unlike my former self, I actually tested all this code. So, and also let me add this. You gotta define tuple element anyway because it's in the standard. So if I need to go through the effort of defining it, why not avail myself of it? And second question was, why don't I use composition instead of inheritance here? I mentioned this empty base optimization. which goes like this. So, you recurse here to a smaller tuple until you get to the empty tuple, right? If we used, if we chose to simply store it, what would happen is that the empty tuple is going to require one extra word in the implementation, which is going to essentially, we have tuple of int and int, and it's 3 words instead of 2. So that would be an unacceptable overhead. There are other techniques to deal with this, but I chose what fits in slides, right? Yes, Stefan.
Actually, in VC 9, SP1, and 10, we actually did store an extra 4 bytes in tuples that we squeezed out in VC 11. So hopefully people will notice that. I just want to mention the restriction on not having parameter packs expanded as data members makes life intensely painful for standard library implementers, as you can see here. But if you're just an ordinary user and you want an expanded variable number of data members, use a tuple. You can leverage this implementation. It's only when implementing tuple yourself that you've got to do this crazy base class stuff. So life's not as terrible as it looks.
So to sort of echo what Stefan just said, number one, we don't do something outrageous, right? They fixed adding the extra word that shouldn't be there. And number two is essentially, how should I put it? Let me go back here. Skip the guy real quick. Skip the bad guy. Okay, good. All right. So here, so we have we have 6 rules that tell you where you can expand things. And to people's chagrin, including myself and Stefan, it seems this list is rather limited. You can't expand at top level, for example. You can't expand a list at top level, which is a sort of a something that again makes life painful to some. There are techniques that essentially, again, it's the sort of that enables things. It doesn't necessarily make them super easy. As an example, for example, there's no top level here. You can't say I'm going to call a function, apply it to multiple arguments, and just put it there because it returns void. You can do that if you wrap everything in a function that does nothing. And I presume this is going to become a used idiom. Like, I don't know what the name would be. Do nothing? Identity? I don't know. Like kind of just expand. Avoid a restriction. And it's going to essentially wrap a call to a function that does the Variadic thing. And that's going to work. If you remove that function, it doesn't work because the expansion is not allowed.
Andre, there's a question from Twitter. Can you
yes.
Take that one?
I once make a tupleite struct that ordered types by size. It made for smaller structures because of alignment. Is this used? Excellent. All right, so Twitter is better than us. All right. For 2 reasons. Remember my first slide. So the answer is this is a good idea to do. It's a good thing to do. The more general thing to do would be to solve a sort of a backpack problem, right? Knapsack, whatever. The NP complete thing, which is figure out what's the best way to put the things in a knapsack to essentially minimize the loss due to alignment and padding, right? Order them by size is a good approximation of that. I couldn't fit that in one slide. It's rather difficult to do. It's doable, though. And I mean, obviously, Twitter implemented it, right? So it's a good idea, yes. Andre, when I tried to implement a tuple iterator, my problem was that each ++ returns a different type and C++ is statically typed. It's a feature, it's not a bug. So here's the thing. You cannot use anything variadic with the classic line of thinking which uses iteration and mutation. Right? It's all functional, it's all recursion. There's no way to say, let me use ++ and essentially iterate through a tuple. The way it works is you must use either some sort of like boost MPL does, or recurse. So there's no sort of straight iteration with ++. Questions? Yes.
So now we have this Variadic number of template parameters. Can I do something with part of that parameters? Let's say with half of these parameters do something one operation and another
Right.
operation for another half.
Right. So question: can I take a slice of the Variadic templates and use it? Actually, you can. It's highly non-obvious how you can do it, but essentially you can say, well, I want to take from type 3 up to the end with a recursive template. It's not easy, but it's doable. And people are doing it. We do it at Facebook. We have in our code base, we have something that gets you, for example, the last element in a parameter pack because we just need that guy. And it turns out GCC optimizes everything very nicely, although it's all recursion and stuff. It figures out, oh, this guy wants the last thing, so it does it. Slicing these parameter packs, I think, is a good thing to do. It's an interesting line of thought. It's an interesting direction. We gotta, yes.
So right there you have a list of T's and U's. And I'm curious what happens if the length of T's and the length of U's are different.
What happens if I try to expand in lockstep, I assume, right?
Right.
T's and U's and the size are different. Compile time error, which is going to be a little novel by Oscar Wilde. It's just going to be. That's what's going to happen. Come on, Twitter. What's happening? All right, question. There are a few more. We have like 3 more questions to go, I think.
Andre,
Yes.
is there any support in between like using std tuple with sequences in the Boost Fusion namespace? For example, for like invoking functions with a tuple that will expand that tuple into its the arguments of the function and then call the function.
So does tuple support automatic expansion? Such as I have a tuple of, simple example. Let confirm if I'm understanding your question. So I have a tuple of 3 integers, and I have a function that takes 3 integers, right?
That's correct.
Can I actually expand the tuple into the function, right? This is the question?
Yes, that's the question.
All right. The answer is no. You can't. And this actually is what I consider a large shortcoming in the design of tuples. It's actually impossible to do so. It is possible via very complicated templates, which can be written. I sat down and wrote them. It's extremely difficult, though. And expansion is not, and composition in general is not easy to do with tuples. So unfortunately, I must say let's say it's doable, but not really easy at all. Sorry about that.
Okay, we have time for one more question.
One more question. Depends how fast I answer. We have 2 minutes. Bartosz. Yes. Yell. Yeah, I'll repeat the question. Yeah, he's going to destroy.
No, this is probably related to the previous question. I was trying to implement something like a map algorithm that takes a list of types and returns, let's say, a list of types with, pointers to these types.
Right.
Right. But there is no way to return a variadic tuple.
Right.
Or, pack. Right.
Yes.
Is that the same problem?
Yes. Let me actually go back here. All right. So the question was, and let me know if I got it right. Essentially, these parameter packs, be they type or values, they're not first class at all. You can't say, I want to transform this list of types and obtain another list of types and give it back. Likewise, I cannot say I'm taking this list of values, do some processing and return another list of values. This is not possible because of this exact problem. There's no first class quality in parameter packs in this list of types and list of values. What you can do, however, you can wrap, and people do that. You can wrap this into, let me invent a name right now, type list. You can say type list of T is my list. So you can actually invent a simple wrapper that simply stores the types, puts them and makes them into an actual type that is first class. it's a real type. It's not a concoction, right?
But you could have done it before C++11.
But you could have done it before C++11. You could not have done it with variable arguments. So remember, in modern C++ design, there's a lot of pain that code must go through to essentially support sort of variadics with all these macros and all that stuff that's fixed now. Similarly, for lists of values, you got to put them in a tuple, for example. So the tuple would be a prime example of that, right? We have 13, 14, 15. We're negative. All right, with this, thank you very much, and I'll be at the panel.
Andre. Awesome.